In this chapter, we're going to start delving into acid-base equilibrium specifically. So we've already talked about equilibrium, so a lot of the concepts we've already covered are going to come back into this chapter, but part of it's more background, part of it's more foreground, but all of it's important. We've also learned about acids and bases in first semester, and all of that comes back as well. So this chapter is pulling in some new concept, yes, but a lot of this you've seen before. We're just not going to delve into the system specifically of acids and bases and start applying things we've already learned into this specific world. So will there be new concepts? Yes. But will there be a review of a lot of things we've already learned and maybe pulling it back and applying it in new ways? Yes. So first, modules, some of them got a lot of objectives. And so this one's actually kind of short compared to a couple that are coming. But I've tried to break them up the best way it makes sense. Some of these videos will be longer just because there's not a good way to break it up. So pause if you need to, watch at whatever speed you need to, etc. But just realize that some of these modules are a little bit longer than I normally prefer just because there's not a good way to break up the content. For that, I apologize. This first module, we're going to talk about the three main acid-base theories. We have the Arrhenius, the Bronsted-Lowry, and the Lewis. We've talked about Arrhenius acids, bases, Bronsted-Lowry acids and bases, and Lewis acids and bases in first semester general chemistry. But now we want to bring them back and really start delving into these types of systems. Arrhenius definitions are always valid, but it's more used in Chem 1 than Chem 2. In this chapter, we're really going to delve a lot more into Bronsted-Lowry and a little more into acid, and then we're going to see how Lewis acid-base theory applies a lot more as we go on into organic as well. You should be able to define a Bronsted-Lowry acid and base and the conjugate acid-base pair. Bronsted-Lowry has this concept of a conjugate acid-base pair. They're always coupled up. You need to be able to, if you're given any acid or base, you should be able to tell me the conjugate acid or conjugate base for that system. You need to be able to identify any Lewis acid and any Lewis base. You should also, of course, be able to identify Arrhenius acids and bases, but again, that was directly taught in Chem 1, and we're pulling that back. Identify your hydronium ion. You need to know that hydronium is H3O+. Recognize the term H+ and H3O+. We use these interchangeably. So H+ we use in place of H3O+. But H3O+ specifically is known as the hydronium ion. And be able to identify amphoteric substances. What do we mean by amphoteric? It's a substance that can behave as an acid or a base. You should be able to write two equations. Some have more than two. If you have a triprotic, you can actually have more than two. For amphoteric substances in which it behaves as an acid and in which it behaves as a base. So our definitions. Let's go back to Gen Chem 1 with our Arrhenius definition. The Arrhenius definition tells us that an acid is going to produce H+ in solution. So for example, HCl, hydrochloric acid, is one of our strong acids. HCl in solution forms H+ ions and Cl- ions. It produces H+ in solution. We're told that bases produce hydroxide or OH- in solution. Let's use sodium hydroxide, common base source. We know that this splits apart into Na+ and OH- ions in solution. This is a base because it's producing OH- in solution. We can also have a neutralization reaction. Neutralization happens when you have an acid plus a base, and this gives you salt plus water. If we use the two that we've already used, HCl plus NaOH, HCl aqueous plus NaOH aqueous, or hydrochloric acid plus sodium hydroxide, we actually produce sodium chloride and water. Now, sodium chloride is table salt, so we all think about it as a salt, but remember, whatever we produce here is forming a salt. A salt is when you have an ionic compound soluble in water, the cation is not H+, the anion is not OH-. That is a salt. And we can see the pictures here as well. An Arrhenius acid produces H plus ions in solution. An Arrhenius base produces OH minus ions in solution. These again are definitions from Chem 1, but you need to have these in the back of your head at all times. These are the base definitions of an acid and base. Now we do want to delve into a little more specific, looking at Bronsted-Lowry and Lewis. Bronsted-Lowry definition is used in general chemistry too and beyond. In the Bronsted-Lowry world, an acid is known as a proton donor. A Bronsted acid must have at least one ionizable proton. What do I mean by ionizable proton? I mean a proton that it is readily going to lose. It's happily going to give up that proton. It's easy to form a proton that's an ion, specifically H plus. It's a proton because remember H plus, if I lose its electron, all it has left is a proton in its nucleus. Neutrons we're not talking about neutrons here, just protons and electrons. We lost an electron, it forms a proton. It's also ionizable because it formed an ion. At least one hydrogen atom is attached to an electronegative atom, oxygen, nitrogen, or a halogen. Any material that has a proton can potentially be a Bronsted-Lowry acid. Due to molecular structure, often one hydrogen in the molecule is much easier to transfer than the others. So we need to pull back in chapter 10 and chapter 11. We start looking at the geometric structure of these as well and see how likely is it to lose that proton. Is it stabilized by resonance if it loses that proton? Perfect example here is acetic acid. I write acetic acid as CH3COOH. Many of you, and I write acetate as CH3COO-. Many of you will write acetate as C2H3O2-. While that's not incorrect, it's not helpful because it doesn't show you the structure. I write it in this form because it shows me the structure of how it's put together. So acetate has this carbon with 3 hydrogens attached to it. That carbon's attached to another carbon, which has 1 oxygen and then 1 OH-. Why is it acetate? Because it has a -1 charge. Truthfully, this originally started out as acetic acid. It just lost this proton. Why did it lose that proton? Because if I draw it with the proton missing, if I actually draw acetate instead of acetic acid, hopefully you can recognize that this is going to form a resonance structure. So let me actually draw it a little bit smaller so we can see the resonance structure. This is going to form a resonance structure with this. This has a -1 charge, has a -1 charge. If you want to draw your lone pairs in here, you can. These are equivalent. These are resonance structures. Technically speaking, this molecule, acetic acid, has multiple hydrogens. 1, 2, 3, 4 hydrogens. But note that we're only going to lose the 1 hydrogen to form acetate from acetic acid because it's resonance stabilized. So, due to molecular structure, often 1 hydrogen in the molecule is much easier to transfer than the others. Some examples, how can we say that these are a Bronsted-Lowry acid? Well, if I have HCl, we just talked about how HCl, you can draw it like that or you can just put it together. That was just showing the bottom, but you can, if you're already talking about HCl, forms H plus and Cl minus ions in solution. It produced a proton. It donated a proton. The HCl donated a proton to solution, leaving behind the Cl minus. That is a proton donor. Nitric acid, same thing. Forms H plus and O3 minus. It donated a proton to solution. We're also going to talk about it in another section, but we have diprotic and triprotic. H2SO4 is a diprotic. it can eventually donate 2 protons and form SO4 2-. We also have phosphoric acid, which is a triprotic. H3PO4 can donate all 3 protons and form PO4 3-. Now, it doesn't happen at one time. It doesn't donate all those protons at the exact time. There's different points in the reaction where we'll donate all 3, and we're going to talk about that. Some protons are easier to remove than others, but they can, and it's diprotic, meaning 2 protons, triprotic, meaning 3 protons. So HCl is acidic because the chlorine allows water to steal the proton, forming hydronium ions and chloride ions. Nitric acid is acidic because the nitrate allows water to steal the proton, forming hydronium ion and a nitrate ion. Water is acting as a base here and accepting the proton. So even though we often write the reaction like this without the water shown, we can also write it like this, where we show your acid and your base where water's acting as a base. So if I write it out like that, HCl plus water, I see this forming H3O plus and Cl minus. And yes, this is what's written in the box. But this has accepted a proton. We'll talk about that in the very next slide. Bases accept protons. And now we see it's got a proton. This has donated a proton. And we see it's missing a proton. Bronsted-Lowry definition has what we call conjugate acids and conjugate bases. It means going in the reverse direction. Your conjugate acid was originally a base. If I went in the reverse direction, it would act as an acid. In the reverse direction of this reaction, this would be donating that proton. All acids have a conjugate base. If I went in the reverse direction, this would accept a proton. So Bronsted-Lowry bases, a proton base acceptor. A Bronsted-Lowry base must have at least one lone pair electron to accept that proton. Remember, the proton is coming in with no electrons. It needs somewhere to bond to. Bonds are formed through sharing of electrons. So I need to put those electrons somewhere. It needs to have a lone pair to allow those electrons to bond. If it doesn't have a lone pair, if it only has bonds, the electrons are already taken up. It cannot bond to another proton. Because of the molecular structure, often one atom in the molecule is more willing to accept the proton transfer than another. For example, ammonia, NH3, you need to know ammonia. You should know ammonia. It's very similar to ammonium. The difference is ammonia is not an ion, it is a weak base. Ammonia is basic because the ammonia will steal a proton from water, producing ammonium and hydroxide. In this case, water is acting as an acid and donating the proton. Water is amphoteric. Water can act as an acid or a base. So you've got your ammonia, and you've got your water. It forms ammonium, and hydroxide. That ammonia accepted a proton. And this cartoon here, this is website, or this actually, it's a girl, she goes by the Bumbling Biochemist on Twitter. I really like her page. She also has a website. So I highly recommend you check her out. Her stuff is very, very good. But she makes these cartoons of all kinds of different systems for general chemistry, organic chemistry, and biochemistry, where she just explains them in a different fashion, which make more sense to a lot of people. And I really like her content because it just kind of simplifies down complex concepts. So the way she explains the acid-base situation is with Cookie Monster. Say you have a cookie jar that's partially full and you invite over some friends. Strong acids come with cookies they really want to give away, regardless of how full the jar is. Weak acids come with cookies, but they'd rather keep them to themselves unless the jar is running really, really low. Strong acids always donate their protons. Weak acids will donate the protons sometimes. How do we know? Well, we can measure different properties of the species itself. We can look at the structure, etc., and we can determine based on years of measurements that people have done and now values we can provide to you how strong an acid is and how likely it is to give up that proton. Bases are things that will take the protons. So strong bases will always take the proton, will always take the cookies, no matter if the jar is low or not, whereas weak bases will take the proton sometimes. Ammonia is a weak base. It's going to take the proton if it's possible, but if there's not very many protons around, it will wait. At the end of the night, how many cookies are in the jar? It depends on how many each type of friend there are. So amines. We've talked about amines in first semester. An amine is when you have a nitrogen with something bonded to it. R means either a carbon, hydrogen, some kind of carbon chain or hydrogen. Ammonia is an amine. Because it has that nitrogen. NH4, ammonium, is the conjugate acid of NH3. We've added a proton, therefore we now have the conjugate acid. The lone pair of electrons on the nitrogen atom is the basic part of the amine. It's what's going to steal that proton or accept the proton from a different species. So it steals a proton to form a covalent, meaning shared electrons, an H bond that results in a +1 formal charge on the nitrogen atom. We have a +1 charge now. Ammonia will accept a proton here, forming ammonium, and this will be plus charge. Methylamine, we've got a nitrogen group here with 2 hydrogens. This is a methyl group. Call this methylamine. This will accept a proton here and form methylammonium. Pyridine, same thing. We'll accept a proton here, giving this nitrogen a +1 charge. So how did these conjugate acid-base pairs come into play? Well, the conjugate acid-base pair always happens. We always have it happening when we have a Bronsted-Lowry acid-base pair. Because Bronsted-Lowry specifically involves the transfer of a proton. This differs by 1 and only 1 H+. It's the transfer of 1 proton. So we see here ammonia and ammonium. The difference here is 1 proton. Ammonia is a base. It can accept a proton. Ammonium is its conjugate acid. The conjugate acid, because it's an acid, can donate a proton if it goes in the opposite direction. Water, in this case, the water on this side is acting as an acid. Hydroxide is a base. I could also have H2O going to H3O+. In this case, this is acting as a base, and this is my acid. Notice it's per one direction. I'm not combining these two systems. That's not happening. I'm saying one direction, which is it acting. This is the base, is the conjugate acid. The conjugate's always the resulting piece. So here we combine them together, combine these two reactions together. They don't happen individually. Like, I can't just do this reaction. That's not going to happen, right? I don't just have protons just randomly in a jar somewhere. I cannot create nor destroy things. I have to balance reaction. So what happens is I see that I have the two pieces of the reaction coupled up to one another. The ammonia is my base. It accepts a proton from the water to form ammonium, which is my conjugate acid. The water is my acid. It donates a proton to my base to form a conjugate base, hydroxide. So hydronium ion, H3O+. We also call this H+ or proton. H3O+ means the exact same thing as H+. So we can say the concentration of H3O+ is equal to the concentration of H+. We're going to talk about pH in the, I think it's actually the next module, but we're going to find pH is equal to the negative log of H3O+. This is the same as saying equal to the negative log of H+. An amphoteric. Amphoteric is a solvent that can both donate and accept a proton. Basically, it acts as both an acid and a base. Water does that. Water can act as an acid and donate a proton, or it can act as a base and accept a proton. So truly what's often written as is two water molecules will react to form H3O+ and OH-. One of these species acted as an acid, the other one acted as a base. And if we want to write out a little bit slower just to see, we can say H2O plus, let's change the colors, H2O. This is going to act as an acid. We'll have this act as a base. Acids are going to donate a proton, so we're going to form OH-, which is a conjugate base. And the base accepts a proton, forming a conjugate acid. So let's write the formula of the conjugate acid or base for each species. Water is amphoteric. Water, conjugate acid, meaning it accepted a proton. It's now going to act as it accepted a proton. Water acted as a base, accepted a proton. Now it's H3O+. Or the conjugate base. Conjugate base would mean it was originally acting as an acid, so it donated a proton. It's now OH-. And H3, the conjugate acid, would be assuming that it originally acted as a base. It's going to form NH4+. It's not happy about it, but if I originally treated that NH3 as an acid and forced it to behave as an acid, meaning I forced it to give away one of its protons, its conjugate base would be NH2-. HCl3 2-. HCl3 2- can act as a conjugate acid, or can have conjugate acids, meaning it can act as a base to start. If it acts as a base, it has a conjugate acid. It could form HCO3-. It could also form H2CO3. Now, it doesn't have a conjugate base because conjugate base means it would act as an acid in the first place, and it doesn't have any protons it can lose. So it can't act as an acid in the first place and lose any protons. H2PO4-, If it's acting as a base, it's accepting a proton, forming a conjugate acid, H3PO4. If it's acting as an acid to form a conjugate base, it's going to lose a proton. So it can form HPO4 2-, and it could go one step further and form PO4 3-. So again, to go to here, water acted as a base. To go to here, water acted as an acid. Here, ammonia acted as a base. To go to here, ammonia acted as an acid. Here, carbonate acted as a base. And here, it can't do anything because it doesn't have a proton to act as an acid. Here, H2PO4- acted as a base. And here, H2PO4- acted as an acid. Practice these, you should be able to identify the conjugate acid or base or both for any species we give you. If it has a proton, it can theoretically act as an acid. It can theoretically donate it. Will it? Depends on the system. But theoretically, if it has an acid, it can donate it. If it has a lone pair, it can act as a base and accept a proton. So ask yourself, does it have a proton? If it does, it acts as an acid. Does it have a lone pair of an electron? It can act as a base. Is it amphoteric? And if it's amphoteric, is it acting as an acid or a base? It can do both. Even regular ions could act as an acid and or a base depending on their system, as demonstrated by carbonate. Specifically, bicarbonate can do that, and we see with the phosphate system. We also have Lewis acid-base theory. So a Lewis acid is called an electron pair acceptor. In organic, you're going to hear this called an electrophile, and it's a very important term. It's electron deficient. It wants to find electrons. A Lewis base electron pair donor is known as a nucleophile. In order to be a nucleophile, it must have a lone pair of electrons. So Lewis base provides electrons to form a covalent bond with a Lewis acid, who's seeking out those electrons. Nucleophile plus electrophile gives you this product that we call an adduct. All Arrhenius acids and bases can be defined with Bronsted-Lowry as well, and with Lewis acid as well, along with the Bronsted-Lowry can be defined under the Lewis acid-base terms as well. So we see here an H+, Bronsted-Lowry model focuses on the proton. Lewis model focuses on the electron pair. The ammonia is donating a pair of electrons to that H+. That H+ is accepting to be able to form a covalent bond with the ammonia to form ammonium. Remember, a little bit of a review from first semester. A strong acid completely ionizes an aqueous solution, but a weak acid only partially dissociates. So HCl is a strong acid. This forms H plus Cl minus. We can also write this as HCl plus water, giving me H3O plus Cl minus. This is my acid. It's forming a proton. It's my Arrhenius definition. This is my acid. It's donating a proton. This is my conjugate base. This is my base. It's accepting a proton. This is my conjugate acid. CH3COOH, we write this as an equilibrium because it partially dissociates, forming CH3COO minus plus H plus. It's an acid because it forms H plus in solution. I can also write this with water. These are aqueous. This is my acid, my base, my conjugate base, and my conjugate acid. Now, why do strong acids dissociate completely, but weak acids only partially dissociate? Stability. Strong acids want to get rid of those protons because their conjugate base is so stable in solution that it's fine not having a proton. Weak acids will partially dissociate because although its conjugate base is very stable, it's not as stable as Cl minus or any other strong acid whose conjugate base is very, very stable. Acetate is still fine accepting the proton. It depends on the pH and it depends on how many protons there are in solution. If there's a lot of protons around, yeah, it'll take one. But it wants to make sure that everyone has its fill first. It's all about stability. So we're going to talk about this more at the end of the chapter. But the strength of acids comes from the stability of their conjugate base. And the more stable that conjugate base, the more likely it is to give up that proton. Cl minus, remember we learned about this in first semester. Chlorine is a halogen. Halogens need to gain one electron and they can be just like a noble gas. That's their goal, to be like that noble gas. HCl, strong acid, because it's going to give away that proton and form Cl minus. That is the very, very stable conjugate base that doesn't want its proton back. You need to know your strong acids. Any other acid is assumed to be a weak acid, and you should absolutely know that CH3COOH is called acetic acid and is weak. So let's look at a quick example here. Which of the following acids has the smallest Ka value? Ka, I know I have not clearly defined this yet. Ka is very similar to Kc. The difference is A stands for acid. We calculate it the exact same way. It's the concentration of products divided by reactants. So if I was to look at, say, acetic acid, CH3COOH, this does form an equilibrium because it's a weak acid. Weak acids, weak bases form equilibriums. Strong acids, strong bases form complete reactions because they completely dissociate. Weak acids, weak bases form equilibriums. This will form acetate and H plus in solution. If I wrote the Ka, H plus and CH3COOH. How do I have a smaller Ka? A smaller Ka means less product, more reactant. Smaller Ka means weaker acid, less dissociation, or ionization. The way these molecules are written, this is a complete molecule. This is ionized. So you want to find the system that has the most molecules still together. Here I've got two molecules together versus two separate. So the Ka would be equal to 1. Here I've got 1, 2, 3 molecules together versus one molecule separate. So this is like a 2-to-2 ratio. Just showing you, I mean, I know it's not mathematical, but showing you the distribution of them. This is like saying 1 to 3. And this one molecule together. 1, 2, 3 apart. Acid 2 is going to have the smallest Ka because it's got the smallest amount of product, the most amount of reactant still present in the system. Bases, a strong base completely dissociates in aqueous solution. Weak bases only partially dissociate in aqueous solution. Partially means equilibrium. So NaOH in solution is going to form Na plus ions plus OH minus ions. Whereas ammonia, it forms an equilibrium. You should know this is called ammonia. Ammonia forms ammonium and hydroxide. Again, this is your base. So this is your conjugate acid. Because this is a base, water's acting as an acid and forming a conjugate base. You need to know your strong bases. Remember, you can find those on the table. They're grouped up nicely on the table, and any other bases not listed are assumed to be a weak base. So strong bases dissociate 100% in water, weak bases only partially. Your amines are weak bases. Are they your only weak bases? No, but they're a huge portion of this class. Remember strong, group 1 and 2, metal hydroxides. Not all of them. Lithium down to cesium, calcium down to barium. Beryllium and magnesium hydroxides are not appreciably soluble in water, so they don't act as strong bases. And remember, these grouping here have 2 OH groups for each one. What I mean by that is it's calcium hydroxide, CaOH2. Strontium hydroxide, SrOH2. Barium hydroxide, BaOH2. Try not to forget that part, okay? Because students forget that all the time. Whereas you've got like lithium hydroxide is just LiOH, potassium hydroxide, sodium hydroxide. I just wrote those in backwards order. Rubidium hydroxide, what's the last one? Cesium hydroxide. All have one hydroxide to the one metal. But these are called your metal hydroxides. These are your strong bases. Anything not in this list is a weak base. Here's some common weak bases with their Kb values. Kb is just like Ka. It's just products over reactants still, but B stands for base. So for NH3, forming NH4 plus OH minus, Kb is equal concentration of NH4 plus times concentration of hydroxide divided by concentration of ammonia. Remember, we do not include H2O because it's a liquid, and it's your products over reactants. It's your ratio. It's your law of mass action. So we can see a bunch of different reactions here and some of their Kb values. And Kb tells us how much is dissociating. A larger Kb value, the more it dissociates. Smaller Kb, the less it dissociates. Larger K value in general. For acids and bases. You should practice these equations, these ionization reactions. Practice them, get comfortable with them. You're always producing, for bases, you're always producing hydroxide. For acids, you're always producing H plus or hydronium ions. But practice these, get comfortable with these concepts because they're coming back heavy through this chapter and the next chapter. We need you guys to understand this stuff. We also have this concept of ArrowPushing. So for ArrowPushing, here's the rules, and then I'll explain what we're talking about. For arrow pushing, always start at the base of your arrow at an electron pair and then travel to where you're going. So this could be a lone pair or a bonded pair. Draw your arrow from the electron pair to point to its destination, which is a more positive atom. You're going to use Gen Chem knowledge of Bronsted-Lowry behavior to determine the reaction. You will learn additional concepts later in organic chemistry for arrow pushing, but this is your first exposure to arrow pushing and we need you to be comfortable with it. How is arrow pushing working? Arrow pushing is basically you're showing how are those protons transferring. So in this case, I see that I've got a base here in the form of ammonia, and I've got, therefore, water's acting as an acid. This is my conjugate acid. This is my conjugate base. What that means is that the water lost a proton to the ammonia. This lone pair comes in and is taking this proton. We are then going to draw an arrow from this bond, which is hard for me to do, from this bond here to the oxygen to show that the electrons that are currently being shared between the oxygen and hydrogen are staying on the oxygen. So I formed this bond and I gave this pair of electrons back to the oxygen. My arrow always starts at the lone pair or electrons that are going to grab that proton. Again, forming this bond. And then this bond between the hydrogen and oxygen, those electrons are left behind on the oxygen. I have an entire worksheet put together with just some different examples of different amines, of different complexes for you to be able to practice arrow pushing. Please, please, please do so. You are responsible for arrow pushing and be able to identify, starting at that lone pair or bonded pair, where does it travel? It takes the proton. Where do electrons go from where that proton was originally bonded? They go to the resulting acid. It's an acid because it's an electron pair acceptor. It accepts that electron pair from that bond and lets the proton leave. It's a proton donor, Bronsted-Lowry definition, electron acceptor, Lewis definition. You are responsible for arrow pushing. So please, please, please practice that.